This is Mr. McCord's chemistry class. We're going to be looking at pH and pOH today. So pH is probably something you've heard of as we've talked about acids and bases. It's one of the ways that we measure how acidic or basic a solution is. The pH scale goes from typically about 0 to 14 is what we use that. And depending on where you lie on that scale, it tells us whether something is acidic or basic. So below 7 means acidic on the pH scale. Above 7 means basic on the pH scale. And the farther down towards 0 or towards 14 you get, the more acidic or basic you get, respectively. 7 is neutral, meaning it is neither an acidic or basic solution. Okay? One of the quick ways we can test for pH is with these nifty little pH strips you can get in the lab, right? Where the color that they change tells you where you land on the pH scale, which is pretty darn nifty. So I've got some pH strips here, and I'm going to test two solutions we have. Okay, the first one is vinegar. All right, that is a solution of acetic acid in water, so we should expect it to be acidic. And then this cleaner over here is ammonia. It should be basic, so we should expect the pH to be above 7 for that one. So let's try these out. So the strips start at about kind of an orangish color. Like this guy. See right there. I'm going to dip this one into my vinegar. And what we get is this reddish color here. And based on that color of red, I can go to the chart and kind of compare it and see where that lands. So I would rate that maybe about a 3, maybe a 2.5 or something like that. But this is acidic, and it's pretty far down the scale for an acid. Set that there. I'm going to test our ammonia next. Look at that. Okay, that is a very nice blue. Actually kind of matches my shirt. See it is on our scale. So kind of matching that up to the colors. I'd say that's about maybe a 10. I'd shoot for 10. Okay. Again, I guess my shirt was made to indicate things with a pH of 10 with these strips. Bad joke. Okay. So pH strips can kind of be used to approximate the pH, the acidity or basicity of a solution. There are other ways we can do this. So we can use acid-base indicators that also change a specific color, but are usually present in liquid form. So we would add in a drop or two into the actual solution and see what color it would become. We'll use those kind of a little bit later on down the line. You can also use a pH meter, which is a fancy little device you can plug into a computer typically, and it will read out exactly what the pH is in the solution. It's got a real fancy way that it does that. So rather than trying to hold the paper up and try to what color is it, no indicator involved, no pH strips involved. We basically just dunk it in there, and then it will give us a number for the pH, 3 or 12 or 1 or 7 or something like that. Now, something that's kind of interesting, acids and bases kind of lie on the same scale. When we are figuring out how acidic something is, we're typically looking at how concentrated it is in terms of H plus hydrogen ions, or as water picks them up, hydronium ions, H3O plus. Okay? For bases, we look at the hydroxide ion concentration, so OH minus. When you put an acid and a base together, well, the H plus and the OH minus come together and make water, which is not acidic or basic, it's neutral. So the pH scale should indicate that. If we combine something that's acidic, like the vinegar that's left over on the end of this pH strip, with something that's basic, it should shove us back down on the scale towards a larger, more basic pH. So we can kind of cancel out the effect of one with another, an acid with a base. So let me try adding this acidic pH strip to my base over here. Yeah. So I've got some kind of greenish blue on the end here, but you can also see the orange where my acid has been canceled out or neutralized with my base. Okay, so I didn't have an even split. I didn't meet right in the middle. I had probably a higher concentration of base, especially over here on the end. Okay, but I can kind of counteract one with the other. They are on the same scale. Okay, and the way that we measure them is therefore related. Okay, so this is our pH scale. Again, goes from 0 to 14. 0 to 7 is our acidic range, and the farther down this way we go, the more acidic it is. And the higher up we go, past 7, means we're getting more and more basic. Okay, so we just looked at two substances. One of them was vinegar, so that landed around a pH of 3 or so. Put that on there. All right, and our ammonia landed about 10 or so. Somewhere. Okay, so we can place a solution on the pH scale to show how acidic or basic it is. And typically, pH is the more common way we do this. Let's talk about what we mean by this pH thing. So, the original explanation of what the P stood for in pH is kind of unclear. The guy that made the pH scale didn't write it down. It could be potential, it could be power, but it's something along those lines. So we're just going to kind of go with power and roll with it. So pH is going to stand for the power of something. That something is H. All right, which for acids is talking about H pluses. That part we do know pretty well. So you can think of the pH scale as kind of a measure of the power or the potential of the H plus ions in solution, which hopefully makes sense since acidity is all about how concentrated your H plus is in your solution. Okay, whereas with bases, we're looking at hydroxides. Okay, now sometimes we're more focused on the basic side of this. So even though there are bases on the pH scale kind of on the other end, it's kind of almost like an afterthought. It's kind of like, well, yeah, it's on the scale, but, you know, if you're a chemist and you're just constantly working with bases, maybe you want them to kind of be the priority on your scale instead of the acids, where you kind of have this early part of the range here. So the pH scale isn't the only way that we can kind of label the acidity or basicity of a solution. We can do it in terms of bases with something called the POH. Okay, where again, if we think of the P as kind of the power or the potential, okay, the OH is talking about the hydroxide ion. So the power of that hydroxide ion in your solution. Grab this blue marker. So we're going to have this scale flipped another way. Okay. Now, I still want to have my acidic stuff over here just because I'm kind of used to it that way. So, on the POH scale, our 0 to 7 is going to be the bases. So it's going to be how basic our solution is. So I'm going to kind of put that over on this end here. Grab these markers. So my very basic solutions on the POH scale are going to be down near 0. Neutral is still 7, right smack dab in that 0 to 14 range. Okay, and something acidic on the pOH scale kind of goes farther past 7 towards about 14. Okay, and of course we can have kind of points in between there. Add some hash marks. Add some little marks here. Okay. So the pOH scale is basically just kind of turned around, where the 0 to 7 range is now for bases, and our 7 to 14 range is now for acids. Okay. Now, whether you are using the pH scale or the pOH scale, you can still talk about acids or bases. It doesn't matter which one. Okay. And the nice thing is, if you are given a pH and you want a pOH, or if you're given a pOH and you want a pH, you can easily convert between the two. Since these are both on a 0 to 14 scale, and essentially the pOH scale is just flipped from the pH scale, all we have to do is flip to the other side of that scale. So if I have something that's a 10 on the pH scale, it would just be a 4 on the pOH scale. Okay? Or if I had something that was a 3 on the pH scale, on the other side, it would be an 11 on the pOH scale. Okay? So we have kind of a connection between the pH and the pOH, since they are on the same kind of size of scale. The pH and the pOH should always add together to make 14. Okay, so if you've ever got a pH or a pOH and you have one, you want the other, it's a pretty easy fix. All right, you're just subtracting one of them out of 14 to see what the other one will be. So for example, a pH of 6 would be a pOH of 8, or a pOH of 5 would be a pH of 9. Okay, so we have a scale that can tell us how acidic or basic a solution is, as long as we can figure out what the pH or the pOH is going to be, and we can convert between those pretty easily. But we're going to run into some problems because we can't always just take a pH strip and dip something in there, or have a pH meter kind of, or a pH probe on hand. So we need to be able to get down to the source of this, what it really means for something to be acidic or basic, which again always comes back to the concentration of H plus or OH minus in your solution. So we can get the pH or the pOH from that concentration of H plus, or that concentration of OH minus. All right, and we can even backtrack and figure out the concentration of H plus or OH minus in our solution if we have the pH or the pOH. So let's look at this. We have two problems here where we've got a concentration of H plus, and we want to figure out the pH, and I have no pH strips or pH probe to use. Okay? I've also got the concentration of OH minus in a solution, and I want to figure out the pOH. All right? Well, first things first, we're going to start using brackets around our H plus or OH minus, just as a quick way to say concentration of. So the brackets just mean molar concentration. It's another way of saying we want the molarity of this, or the molarity of this. Okay? So the concentration of H plus in brackets, in this case, is 0.0235 molar. Right? That's our molarity. We want to make a pH out of that. Now, before I said the P can kind of be seen as a power or potential or something like that. But even though we don't know what the P is like word-wise supposed to stand for, we do know what it means mathematically, and it occurs several places in chemistry. It's actually a little common. So instead of thinking of it as the power of, when we do the math of things, this is actually going to be the negative log of something. Okay, if we're talking about acids, we're trying to get a pH. All right, we would do the negative log of H plus's concentration. Now, specifically, this is a log base 10. Okay, but a lot of times if you just hit the log button on your calculator, it'll know log base 10. It's going to assume that. All right, so the logarithmic scale is good for things that are exponential, the things that jump. So between a pH of 1 and 2, you don't actually have an increase in acidity going from 2 to 1. That is just, oh, it's now 1 pH unit more, and so it's, 1 more. It's actually a tenfold increase coming from this base 10 being tier 2. So every time you go down a unit on the pH scale from 7 to 6 to 5 to 4, you're actually increasing the acidity times 10. So you go from, this acidic to 10 times as much times 10 times as much as that every time you go down a pH unit. Same thing goes for how basic something is as you move up the pH scale. And of course, the pOH scale is just reversed from that. Okay? So if I want to figure out the pH of something, as long as I have the H plus concentration in the solution, like what we looked at for dissociating ions and seeing kind of what the concentration becomes, I just take the negative log of that in my calculator and I get the pH. That's all the pH is. Right? So the negative log, base 10, of 0.0235 is going to be what? H equals log of 0.0235 n. Right? pH comes out to be a unitless number, no units. So we kind of just drop the m for molarity and see what number comes out on the other side. All right. So I need a calculator. Give me a second. Okay. Negative log of 0.0235 gives me 1.629-ish. On the pH scale. So pretty darn acidic. Right? And again, there's no units for the pH. We just kind of drop the molar unit. Big N. Right? This is my pH. All right? All I needed was a calculator. If I know the hydrogen ion concentration, or again, it could come from the H3O plus concentration, same way, I can get the pH. All right? So that should mean that the pOH kind of comes from the same kind of thing, but with OH minus concentration. So let me try plugging in one of those. Again, the P of pOH mathematically is going to stand for the negative log. Specifically the log base 10. So as long as I know the hydroxide ion concentration in my solution, I can figure out how basic the solution is, or acidic, on the pOH scale in those terms. All right? So I'm going to take 0.093. I'm going to take the negative log of that, negative log of 0.093. I get 1.03. That my other blue. OH equals negative log. Gets me 1.03-ish on my pOH scale. And remember that's turned around the other way, so that's a very basic solution. Okay, so cool. I can figure out the pH of the POH as long as I've got the concentrations of those ions, all right? Well, what if I want to go back the other way? What if I have the pH and I want to figure out what my concentration of H plus ions is, okay? Or what my concentration of OH minus ions is. Shouldn't be too hard. All I have to do is undo the negative log thing. Now, if you are a fan of logarithms, you can figure out this math for yourself. We can derive how to get OH minus or H plus's concentration by kind of undoing the logarithm. But this is not a math class, so we're going to kind of cut to it. I encourage you to figure out how it works, but it's not necessary. I'm just going to jump straight to the equations for these. So the H plus concentration of something is going to be 10 to the power of negative whatever the pH is. All right? So if I wanted to switch this back into an H plus concentration, I'm going to take my pH as the negative exponent of 10. So 10 to the power of negative 1.629 should get me my H plus concentration, which we already said was 0.0235. So it should get me back to that original answer. Let's try plugging it in. Okay, 10 to the power of negative 1.629 gets me, all right, 0.02349, which is going to round up to 0.0235. Right? Now, I know this is supposed to be a concentration, so even though I didn't have units coming from this math, I'm just going to kind of stick it on there. Okay? So as long as you've got the pH, you can find the H plus concentration of that solution with that pH. You've just got to take 10 to the power of negative whatever the pH is. We can do the same thing for the hydroxide concentration. Right? Undoing this logarithm means that we can get the OH minus concentration just by taking 10 to the power of negative whatever your POH is. Okay? So in this case, if my POH was 1.03, my OH minus concentration comes from 10 to the power of negative 1.03. All right, so I can plug that in my calculator too. 10 to the power of negative 1.03. And I get about what I started with, about 0.093. The rounding is a little bit different, but it's close enough. Again, I know this is supposed to come out to be a molar concentration, so I'm just going to tag a big M on there for molarity. And there we are. Okay, so we can go back and forth between pH and H plus concentration, between POH and OH minus concentration. But what about some weird cases? Maybe I just go take the numbers off of something. I have a solution with a POH value, but I want to know the H plus concentration in that solution. Well, that's going to be a little bit trickier, but it is possible. Since the pH and the POH scale are both at a 14, I can still make that conversion. So I'm going to show you kind of one last thing that's going to put all of this together in one chart to see how we can bounce between these concentrations and these concentrations for H plus and OH minus, how it all connects together in a solution. Okay, so this can kind of tie all of this together and sort of summarize the equations that we have. So we can go from the H plus concentration to the pH using the negative log. We can go from the uh, concentration of OH minus to the POH using the negative log. We can get back out of both of those by taking 10 to the negative of the pH or 10 to the negative of the POH. And we can go between pH and POH by seeing that they're on the same scale. They should add up to 14, so if we subtract one of them out of 14, we should get the other. Now, if you move on to higher level chemistry, there's actually also a connection here between H plus and OH minus concentration or solution, but that's not, something we can fit in here. That's something for another day if you choose to go on to AP or ACP chemistry or something like that.